reiterate a little bit of it, but what I really want to do is I want to get you guys set up to be able to do some simple center of mass calculations. And again, I kind of blew this in sixth period, so I would really like to do a better job here. And my understanding is that we did not get very far at all on Friday on that, so we are starting fresh. And I am sure that I said something about, remember there is a difference between center of gravity and center of mass, and I talked about tipping things over and all that. Today I want to talk about how do you find the center of mass. And we're going to talk about just what I consider to be a point object calculation. And then we'll talk about how can you tell if your system is a point object calculation or not. So a point object calculation means that we literally have a group of point masses somehow arranged in space, and each one could be of different mass. And let's assume for the time being that this world is a two-dimensional world, but not a three-dimensional world. If you were going to try and find the center of mass of this system, there is a procedure on how to do so. But there's also an equation. Of course, like everything else in physics, it's an equation. And if just having the equation was enough, you would all be experts because you get equation sheets. We know that it's not about the equation, right? It's a method, and you have to understand what the equation does and how the method works. The equation for center of mass is not going to be helpful. It's a summation, because center of mass is what's known as a weighted average. This is the equation for the center of mass, assuming that R represents a vector drawn from the origin to each object in your system. The weighted average would be where the center of mass of that system is. Now, that tells you absolutely nothing. But what I do want you to know is that center of mass is a place. It is a location. It's not the mass of the system. It's where the average mass of the system is located. So that's an issue that many people don't realize, that the center of mass is a location. It is a place. So now that you know that, in your notes, make sure you say that the center of mass is a location. It's a position. It's something. It's a point in space. For a two-dimensional system, we will never do a two-dimensional calculation like this. There's just no way. The math is just not going to work. The way we actually do it is we do it as a series of one-dimensional calculations, meaning we will calculate the x location of the center of mass as separate and distinct from the y location of the center of mass. Now, to understand what I'm saying is we will take all the objects and their location and treat them first as if they are one-dimensional in the x direction, find that center of mass, put that aside, and then treat them differently in the y dimension. To do any of that requires that you do one thing first. Decide where your reference point is. Pick a place, and that's 0. I'm going to pick 0 here, where M1 is. I'm going to make all of my calculations relative to M1. Now, what that really means is I'm going to draw a y-axis that starts at x1 and an x-axis that also starts at m1. And I'm going to make this my reference for the x direction and this my reference for the y direction. Now, calculating the center of mass means that when you're looking at a one-dimensional projection, you simply look at the x-coordinate for every object in your system. I have what appears to be 6 objects. So I will look at, this is x2. That is the distance from the origin to where the second mass is in the x direction. And then I'll have what appears to be x3. That's the distance from the origin to where where m3 is in the x direction. And do I have to keep drawing that, or can you guys get the idea? That when you're dealing with a two-dimensional system, we look at all the locations in the x direction and do that calculation, and then we'll do all the same thing in the y direction and do that calculation. So our problems will always be able to be broken up into one-dimensional problems. So let's look at how do you solve the dimensional problem. And let's just create a simple one-dimensional problem. To make it one-dimensional, I'm going to create a number line. And I'm going to put us together with, say, 4 objects on that number line. Let's say object 1 is 5 kilograms, object 2 is 10 kilograms, object 3 is 2 kilograms, and object 4 is 8 kilograms. Okay? Now, let's say that this location is my reference point, 0. This is 5 meters. This is 11 meters. This is 15 meters. And this is 17 meters. The straightforward way to do this, especially a situation like this where we have been given a reference point, is to do the weighted average that's been suggested. The location of the center of mass is just that. It's a weighted average. It's a summation. And it says to take each mass and multiply by its distance away from the reference point. Then divide by the sum of the whole mass. That's what that ratio is. And that's how you calculate center of mass. So the top is the weighted portion. The bottom divides out by the whole mass. So for this problem, I'm just going to go mass by mass and place it into this formula. For example, 5 times 5. That's the first mass. Got it. Second one, mass 10 times 11. Now I've got that one. Third one, 2 times 15. Got the third one. And last, 8 times 17. I've accounted for each of the masses. Now you have to divide by the sum of the masses. 5 plus 10 plus 2 plus 8. This is how you calculate center of mass. It's not particularly interesting, and it's not particularly hard. This is not really how you'll end up doing it, but this is a good start. Now, the first real application of this is something that we're actually not going to talk about for a little while. I don't care what the number is. I don't really think we have to wait for all of us to type this in, do we? You guys know how to use calculators. I'm not worried too much about it. I know some of you are completionists and have to have an answer. I don't care. So if you want to have that, that's fine. I want to point out something, though. You are given a reference point. You don't have to use the reference point that was given. You can pick the reference point. For example, I almost always choose one of the masses as the reference point and make that 0. If I did, then I would have to correct each of these to figure out where their location is relative to my new reference point. So unless you're given a reference point, you might have to choose a reference point. Let me give you an example. One of the things we will have to do when we deal with orbits is determine the center of mass between the Earth and Moon. Now, what you'll be given is the mass of the Earth, the mass of the moon, and their separation distance. If you want to determine the center of mass, then you treat that separation distance like it's the number line. But you still have to come up with your reference point. Where are you going to measure the center of mass of this system from? Now, if you're told, that's fine. They might give it to you. But oftentimes, they don't. So you might say, okay, I'm going to make the center of mass be relative to the Earth and make Earth 0. That would make whatever the separation distance is, the distance from 0 to the other point mass. So how would this look for center of mass? Well, this would be x center of mass equals mass of the Earth times 0 plus mass of the moon times r, the separation distance, all divided by the mass of the Earth plus the mass of the moon. Center of mass in the Earth and moon. But remember, this is measuring it as if the Earth is 0 on the number line. A more common thing you might have to do is this. And this is where we're really going to start utilizing the calculator now. Imagine that you and 3 friends are all standing, let's go with 2 friends, all standing on a long, wide plank. You're 50 kilograms, one of your friends is 40 kilograms, and your other friend is 60 kilograms. The plank is 10 kilograms and is 10 meters long. You're standing 1 meter from the edge. Your friend is standing 5 meters away from you. And that friend is standing 1 meter away from them. Could we calculate the center of mass of this system? No. Any center of mass calculation should start with the question, can you treat the system as if it's a collection of point masses? So for a problem like this, generally the answer is going to hopefully be yes. But to do so, you have to ask things that are, I think, important. For example, the plank. The plank is spread out over the whole 10 meters. You should ask, can we use the center of the plank as its center of mass? That's an important question and one I would have you write down. Do you know what the center of mass of the plank is? If you do, then yes, you could treat it like a point mass. If you don't, then you have to find its center of mass first. Can you treat objects that have extension as if they have the center of mass at their center? If yes, you can treat them like a point mass. If no, you have to find out what the center of mass is first. For this problem, I'm going to say yes. We can treat the plank as if its center of mass is at its center. Next, are the people appreciably small? Meaning, are they spread out along the x direction in such a way that we can't use them as point masses? I'd argue that the people themselves are relatively narrow, so that in the x direction, we can use their center being their location along the plank. It's a judgment call, but if you're not given any information about their size, it's pretty typical to treat them as if they are also point masses. So that suggests that this problem has, in and of itself, 4 point masses that we'll be using to calculate the center of mass. Is everybody following along so far? I'm trying to go slow, but this is also not likely to show up on the exam, so I don't want to go really slow. Now, the next question is, what do you want to start? Where do you want to start? Meaning, where do you want 0 to be in this system? You can choose anywhere you want, because location of center of mass is a place. We just have to say where it is relative to some point that we call 0. So there are a couple of natural places that might be worth doing. We could make the center of the plank where we measure this from. We could make the end of the plank where we measure this from. I'm actually going to kick this one to you guys. Where would you like to make our reference point? All right, so I heard the 40 kilogram person and the 50 kilogram person. I am indifferent. So, all right, so we'll go the 50 kilogram person. Now, all jokes aside, there is an important detail here. Had we chose the center of the plank, knowing that there are masses on both sides of the plank, I need to remind you, or at least instill upon you, that center of mass is a vector quantity. Objects on one side of the plank would have to be treated as positive, and objects on the other side of the plank would have to be treated as negative. I haven't said that yet before, but since nobody brought up using the center, and you were going to use, the 40, this would come up. But I still think for this first try, we'll use the 50 kilogram person as 0. So, location, center of mass. Start with the fraction. We're going to do our summation. Mass 1, 50 kilograms. Location, 0. Mass 2, 40 kilograms. Location, 5 meters away from 0. Mass 3, 60 kilograms. Location, 6 meters away from 0. Mass 4 is the plank. How far is the center from 0? 4 meters. Yes, it is. So the plank is 10 meters long. This is located 5 meters from the edge. That makes it 4 meters from that guy. Now, that's the top portion. That's our weighted average. The bottom portion is going to be 50 plus 40 plus 60 plus 10. This is not particularly hard. But since Zach brought it up, and I think it's a worthwhile thing to do, Zach should calculate it from the 40 kilogram person. So, in yellow, I'm going to list that person as 0. You guys should step through this with me and see if you can get the same thing. The location had better come out to be the same. So if we make the 40 kilogram person our 0, then our 50 kilogram person is located negative 5 meters away from 0. Our 40 kilogram person is located at 0. Our 60 kilogram person is located 1 meter away from our 40 kilogram person, but on the positive side. And the plank has its center how far away from the 40 kilogram person? I think negative 1 meter, right? All divided by 50 plus 40 plus 60 plus 10. All right. This will be fun. We should get the same answer for both. We won't. We're going to get different numbers, but they should point at the same place. So, this thing. Because this is something that was kind of on your semester exam, although not really, it's kind of. What if each side is length S, so this whole side is length S, and each piece is mass M, and there are 3 pieces? Can you use what you've been taught to find where the center of mass of this system is? Well, the look on your faces suggests no. Maybe some of you. Let's start from the beginning. Can we treat our objects as if the center of mass of each object is at its center? They look uniform to me. It seems to me like we can treat this as 3 point masses. It does feel two-dimensional to me. Does it feel two-dimensional to you? So I think we'll probably have to treat this as if we do the X part and the Y part separately. So we need to find a place that we're going to call 0. Now, I think a convenient place would be like right here, the middle. But I'm going to purposely make you use here to be 0. Now, again, we treat each dimension separately. So in the X direction, I see that there's a point here and 2 points right here. Well, maybe right there, right? Trying to put that they're at the same location, but there's 2 of them, and they're halfway. So this is 0, and this is 1/2 S. And this is in the X direction. So if I needed a simple number line, X direction. Now in the Y direction, I've got a point here, and a point here. In the Y direction, I have 3 points, but they are spread out a little different. Now, doesn't matter which one of these we do first. They're independent, so I'll do Y, center of mass, first. I don't think I'm going to be surprised here. I'm hoping it works out to be at the center because it looks pretty symmetrical. But starting at the bottom, I have mass M at location 0, plus mass M at location 1/2 S, plus mass M at location S. Those are the 3 masses in the Y direction. 0, 1/2 S, S. Everybody okay on that? What's the total mass of the system? 3M. I have 3 masses. They're all mass M. The top of this is 3/2 M times S. And the bottom is 3 times M. 3's cancel, and I get 1/2 S. I am not surprised, but that suggests that the center of mass is along that line. Now let's do the x direction. In the x direction, x center of mass. I've got one of the m's is located at 0. One of the m's is located at 1/2 s, and the other mass is located at 1/2 s. Right? Both of these are at the halfway mark. Divided by 3m. So can we all see that this is going to be 1/3 s? Now, look, there was something else I wanted to do today, and we didn't get as far as I wanted. So I'm going to ask you to do it. I'm going to explain it orally. No, I'll post it. I'll just send it out as an announcement so that you guys have it clear. I want you to try it. I've not given you no homework, so you'll have to do this tonight.